We use inherently meaningless symbols to communicate every day. Although you've probably seen these symbols before you even knew what they were, these symbols don't have any meaning. But we have developed a code called the English language that assigns meaning to these symbols. These symbols are the alphabet that we use to construct more elaborate words that can communicate more information. When using the English language as our code, we can tell someone to look for a four-legged animal that has pointy ears with a code word that consists of only 3 letters. However, the same message can be communicated with different symbols if we change the code. If we use the French language as our code, the four-legged animal would be represented with a code word of 4 letters. By changing the code, we change the meaning of the symbols. Whenever we display words, we must know what language or code is being used so that we can correctly interpret the symbols. While in French, chat means cat, in English, chat means to have a conversation. When we communicate information about numbers, we typically use these 10 symbols as the alphabet for our codes. When we use symbols to represent numbers, we call that code a base rather than a language. Typically, we use a base called the decimal system, which is base 10. The base number tells us how many symbols are in the alphabet of the code. When we know the base, we represent number information by traversing through the symbols in the alphabet, or the base, until we run out of symbols. And then, we can add more symbols to the representation to represent increasingly large numbers. In computing, we use a 2-symbol alphabet. Therefore, we use base 2 represented numbers or binary represented numbers. We can combine the 2 symbols 1 and 0 to represent an infinite set of numbers. So when we represent numbers, we have to indicate which base we are using so that the number will be interpreted correctly. For example, the code word with 2 1s here is 11 in base 10, but 3 in base 2. Just how like CHAT could mean either cat or conversation, depending on the context. We indicate which base was used by appending subscripts to the number. When we write numbers, the value of the number is encoded by both the symbols and the positions of the symbols. While these 2 numbers contain the same symbols, we interpret them as having different values because the symbols are all jumbled around in different positions. This notation is called positional notation. For decimal numbers, the position immediately to the left of the decimal point is assigned a weight of 10 to the 0. All positions to the left of the position are given increasingly greater weights. All positions to the right of the radix point are given decreasingly smaller weights. We find the value of the number by multiplying the symbol by the weight of its position. So we have 1 1000s, 0 100s, 2 10s, 3 1s, and 4 tenths. When we use binary numbers, each position is assigned a weight that is a power of 2. As a quick tangent, this table shows some common powers of 2. Check it out. When we represent numbers in bases besides base 10, the decimal point is called a radix point. The position immediately to the left of the radix point is assigned a weight of 2 to the 0 for binary. All other positions are given their weights accordingly, just like we saw with decimal. For example, the one in the farthest left position tells us to add 1/8 to the total value of the number. The 0 in the next position tells us to add 0 4s. The one in the next position tells us to add 1 2 to the total value of the number, and so forth. Because we must store the bits of a binary number in physical locations in a computer, every component of the computer is designed and optimized to interpret only numbers with a specific number of bits. Number representations that use more or fewer bits would not be understood by the computer. These fixed width representations mean, for example, that when we are operating on an 8-bit computer architecture, that all numbers will be constrained to use 8 bits. Let's look at a representation called 8-bit unsigned binary numbers. This phrase, 8-bit, tells us the width of the number represented in binary, and that we should interpret the number in base 2. The word unsigned tells us that all the numbers we represent will be positive integers, and that we will use the positional notation interpretation of the binary bits. If instead we had a 4-bit computer architecture, we would use 4-bit unsigned binary numbers. The bit width would be different, but we would still interpret the bits using positional notation. More generally, we call this type of number representation n-bit unsigned binary representation.